Today is the first webinar of our new CCS webinar series where we're exploring the new technologies in decarbonizing gas turbines. The first episode is on BASF OASE Blue technology that is presented by Mohamed Anas, who is a Senior Technology and Marketing Manager for OASE Gas Treatment at BASF, based in Houston, Texas. So today's webinar will be structured as follows. First, Mohamed will delve into the technology developed by BASF. And in the second part, we will open the floor for question and answers. And finally, we will also launch a Slido for gathering your feedback on our webinars, so to improve anything you want for the future. So with this, I would like to give the floor to Mohamed for presentation of the BASF OASE technology. Thank you, Mohamed, for presenting today and for your availability.
Right, let me share my screen. Can you see it?
Yes.
All right, okay. So thank you, Nicolo, for the introductions. As mentioned by Nicolo, my presentation today will be on reducing carbon emissions in gas turbine application using BASF OASE Blue technology. So in this webinar, I will start with the introduction on the OASE Blue technology, and then followed by the challenges associated with the carbon capture and storage implementation in gas turbine application specifically, comparing it also with OASE Blue versus generic solvents like MEA solvents. Towards the end, I will be touching a bit on a few potential configurations to further minimize CAPEX and OPEX of a CCS project. Right. Something went wrong here. All right, okay. A gas turbine is undoubtedly the workhorse of many industries and have long been admired for their efficiency and power generation capabilities. However, as we know, as the world progresses towards adopting lower carbon energy sources, one of the major obstacles in the gas turbine operations lies in the emission of the CO2 and trace components in the flue gas stream. The release of these components into the environment has become a pressing issue because of its significant contribution to the greenhouse gases effects to the world, especially on the CO2 component. Combining both natural gas combined cycle or NGCC and coal-based process, power generation sector accounts for the largest share of CO2 emissions in this area. Therefore, the sector is currently prioritizing CO2 reduction as its primary goal to decarbonize the entire energy chain. Recently, we are already seeing a global shift from coal to natural gas-based combustions to generate energy, with more significant rise in LNG investments over the past decades. Although gas turbines are more efficient and emit less CO2 compared to other fossil fuel technologies, their widespread use still leads to significant carbon emissions. Oops, sorry. So to effectively achieve decarbonization targets, CCS technology integration into this flow sheet becomes very critical. So there are several different technologies available for flue gas capture. However, as we know, the most reliable and proven technology is using solvent-based CO2 capture process. So before we delve into the details, I would like to introduce our carbon capture, BASF carbon capture offering under the brand name of OASE Technologies. So other than producing commodity and specialty chemicals, BASF also offers solvent-based carbon capture technology in both pre and post-combustion flow sheet. Our technology is categorized based on color specific for each application. For OASE white, it is meant for ammonia and syngas, which is CO2 capture in this flow sheet. OASE purple, CO2 capture in and H2S component in natural gas and LNG. And then we have OASE yellow and Sulfex for sulfur selective. And then OASE green for biogas application. And the focus of our topic today is on OASE blue for flue gas capture. In addition to this, we also have two alliances with other partners to broaden our offering on carbon capture applications. The first one is HYPEC Technology, which is a joint development with JGC in Japan, which is essentially a high pressure regeneration process, still solvent-based. And second one is on sulfur selective capture under the brand name of Flexorb with ExxonMobil. Right, okay. So OASE Blue was specifically developed to address the need for large-scale carbon capture from flue gas streams, or also known as post-combustion capture. With our extensive expertise and experience in this area, we have successfully developed a highly efficient process that not only requires low regeneration energy, but also boasts a low solvent makeup rate. These attributes will result in substantial reductions in CAPEX and OPEX, and thereby addressing major obstacles in justifying a CCS project investments. As a process licensor, we provide end-to-end solution, including design, operations know-how, solvent supply, and also technical services to our customers. In terms of applications, this technology is able to treat flue gas streams from power generation, cement, steel, and chemical plants. Or in other words, I would say that the technology is able to capture CO2 from any streams containing oxygen compound. So what are the key needs for post-combustion CO2 capture? On the left side, I've listed the desired qualities by the industries on this application. And on the right, you will see how our OASE Blue technology measures up. Starting from the top, OASE Blue is a proven technology with more than 65,000 hours of testing during development stage and with a few commercial references running to date. Combining our expertise in process design and solvent chemistry, the technology can achieve up to 99% CO2 removal rate with wide range of CO2 and oxygen in the flue gas stream. Depending on the flue gas sources, our typical range of solvent regeneration efficiency ranges from 2.5 to 3.0 gigajoule per ton of CO2. With solvent makeup rate of about 0.3 to 0.6 kilogram of amine per ton of CO2. On the environmental aspect, within our ISBL of the technology, we also have a proven emission reduction zone embedded within the process known as OASE Aerozone. Also, we also develop a proven reclaimer concept to address degradation rates together with nitrosamine management when operating a carbon capture unit. So once the unit is in operations, our post-startup service include access to our design software, which is crucial for training, startup, and also troubleshooting of the unit. In addition to this, customer also has access to our solvent analyzer software, also known as OASE DigiLab, which is actually very important for customers to monitor and track their performance in terms of their solvent qualities to maintain a smooth operations of the carbon capture unit. On the supply chain perspective, BASF is the only technology providers that offers technology and chemical supply to a customer giving assurance on the solvent supply security in the long run. So this is a snapshot of how OASE Blue process scheme looks like, showing all the major equipments in the CO2 capture block. So the raw flue gas comes from the left, and depending on the sources, this stream often need to go through some sort of pre-treatment units to remove trace contaminants like SOx, NOx, particulates, and etc. Typically, at minimum, there is always a DCC or a direct contact cooler column, functions to reduce the temperature for a better absorption process in the capture sections. And also the second function is to polish or to have a final polishing of the contaminants before the gas enters into the absorber. Once in the absorber, the gas is in contact with the solvent to remove CO2 over mass transfer packings. Then the gas travels up to the emission reduction zone, known as OASE aerozone, as mentioned in the previous slide. And before exiting the top, the gas will get cooled down in the backwash section, and also at the same time minimizing the solvent losses going to the environment. Going to the liquid side, the loaded solvent at the bottom is transferred to the regeneration section to strip off the CO2 in the solvent before it is recycled back into the absorber. Given the presence of oxygen in the feed, the solvent will always experience degradation effects, and to counter this, there is a need to include a reclaimer unit to clean up the solvent continuously.
It's okay. You can talk because I'm just listening to a webinar.
Is everything okay? Right. Okay. So now that we have covered the technology, let's talk about the challenges associated with CO2 capture in gas turbine application. Flue gas coming off from NGCC exhaust is generally cleaner than coal-based power plant, having mostly NOx concerns. While these can be addressed in the pre-treatment sections, the bigger challenge affecting the design and operation of a capture unit in this application is low CO2 and high oxygen concentration in the flue gas stream. As we know it, in NGCC application, CO2 concentration ranges from 3 to 6 mole% in compared to coal-based power plant having a higher CO2 content up to about 15 mole%. A low CO2 partial pressure means reductions in driving force for absorption capacity and kinetics. Main impacts observed when comparing generic solvent over OASE Blue are, the first one is larger absorber diameter, higher solvent circulation rate, and also higher solvent regeneration energy. Secondly, the presence of higher oxygen content in the NGCC has a significant effects on degradation rate in compared to coal-based power plant having a lower oxygen content, about 3 to 8 mole%. Oxygen in the feed actually will accelerate the solvent degradation rate, where oxygen reacts with the amines to form heat-stable salts. And this process is also known as oxidative degradation. To mitigate this effect, it is crucial to employ a solvent that has resistance to oxygen degradations, allowing for a long-term OPEX savings when running a CCS facility. Quite a few comparisons has been done in the past, and OASE Blue technology has shown to achieve at minimum 20% savings in regeneration energy with more than 70% solvent makeup rate savings over generic solvents like MEA, depending on the application. Next challenge is on the capture rate efficiency. As CCS about to take off, there have been a push in the market to shift the capture rate benchmark from 90% to 95% and even up to 99% in certain applications to meet net zero targets. Fundamentally, Doing so is possible. However, this would be at the expense of higher regeneration energy, higher solvent circulation rate, and also a bigger absorber diameter, impacting feasibility in justifying a carbon capture projects. On the slide, you will see a plot showing the trend effect of higher CO2 capture rate against regeneration energy in a solvent-based capture unit. Up to about 95% capture rate, the energy increment is gradual and relatively small. However, beyond 97% or about 98%, the energy trend spike upwards, resembling a hockey stick, what we call as a hockey stick shape in a low CO2 concentration application like gas turbine application. This data is also being supported by a theoretical study. In fact, there are also others. In this case, it's based on 38% MEA solvent strength with 4 more percent CO2 in the feed. And this study was actually published in the International Journal of Greenhouse Gas Control. In the reference, you can see that. And in this study, what they found, the analysis indicated that the utility cost or the steam to regenerate the solvent is the biggest cost when capturing between 90 to 98%. But as the capture rate exceeds 98%, this changes to the absorber diameter as the primary factor influencing the overall cost due to significantly higher solvent circulation rate to achieve a very high capture rate. To enhance cost reduction in executing carbon capture and storage CCS project, several measures can be implemented in the flow sheet to improve the energy efficiency of a solvent-based unit. Firstly, is to recover heat at the interstage cooler in the compression train to offset regeneration energy in the reboiler. Or this can be a challenging task due to a low heat grade quality recovered from the train. There are a few compressor vendors already looking into making this configuration feasible. Secondly, there is also an option to do a lean vapor compression, where in this case, the lean solvent at the bottom of the stripper is flashed into an additional flash drum with a reduced pressure in compared to the pressure in the stripper sump. The flash gas is recompressed by a one-stage compressor to the pressure level in the sump to reduce reboiler duty. Essentially, this actually is a play or a trade-off between heating media costs or the steam costs versus electricity costs on site. And the third option is actually to utilize and integrate waste heat available into the carbon capture block to reduce energy, to reduce regeneration energy in the reboiler. For these options to be effective, it is required to optimize the entire flow sheet, especially in NGCC application where HRSG is also recovering heat from the exhaust gas. Based on our experience, these improvements can result in energy saving ranging between 0.2 to 0.5 gigajoule per ton of CO2. And to put this into perspective, a reduction of about 0.1 gigajoule per ton of CO2 in a 1100 megawatt power plant would equate approximately 37 tons of LP steam an hour, which translated to about 0.5% of the facility electrical output. Okay. So taking a step forward, there are also ideas in the market to increase CO2 concentration in the flue gas stream, which will result in a more efficient and optimized solvent-based unit in gas turbine applications. However, implementing these changes or this configuration can be somewhat intricate because it has multifaceted parameters consequences to the whole flow sheet. Therefore, in order to make this possible, it is crucial for everyone to work together to conduct a thorough economics evaluation to quantify the actual advantages of these proposed configurations. The first idea is to consider installing a supplemental firing unit at the outlet of the gas turbine to burn additional fuel using oxygen left over in the stream. By doing so, the oxygen will reduce, while CO2 will increase to about 10% in the flue gas stream, resulting in a higher driving force for CO2 capture process. And this will make the CO2 capture block smaller in terms of cost. However, the extra fuel used in the supplemental firing decreases the overall efficiency of a power plant because energy generated will be from the steam cycle, which is less efficient than the combined cycle process in the NGCC flow sheet. In terms of the limitation, what we see is this configuration actually will result in a higher inlet temperature into the HRSG, limiting the type of material to be used in the flow sheet. The second idea is actually looking into what we call as exhaust gas recirculation, which actually involve recycling a portion of the exhaust gas to the compressor and mixing the stream with the combustion air after cooling and condensing out the water. As EGR, this is what we call as EGR. So as the EGR ratio increases, oxygen content gets diluted in the combustor, and these will produce more carbon monoxide and also unburned hydrocarbon, which need to be dealt in the CO2 capture sections. With these configurations, the CO2 content can increase to about 6.5 mole%. However, this is actually limited at about 40% of EGR ratio due to the flame stability issue in the combustor, which we know it should be ranged between 14 to 16 mole% of oxygen. The third idea is to further upgrade the previous EGR flow sheet in which CO2 membrane is installed either in parallel or in series with the CO2 capture plant. And as you see on the screen there, in this case, it is actually in parallel. And this configuration is known as selective exhaust gas recirculation. The membrane functions to actually concentrate the CO2 and decrease nitrogen in combustion air, which to be recycled back to the inlet of the compressor. By doing so, the CO2 concentration going into the capture plant can range from 14 to 18 mole% while maintaining at about 16 mole% oxygen at the inlet of the combustor. As you can see, the configuration now is getting more complex with more parameters to control on membrane, to control the membrane operation and also as well as the CO2 capture unit. So this complexity may impede operational flexibility due to many process integrations within the flow sheet, which need to be evaluated as a whole. So to demonstrate the cost implication on OASE Blue unit, I actually have simulated a 1,500 tons per day carbon capture and CCS plant using OASE Blue technology to show possible cost savings. So by increasing CO2 from 4 to 8 mole% and decreasing oxygen from 13 to 7%, the reboiler duty and solvent makeup rate can reduce by about 15 and 50% respectively. And from the CAPEX perspective, the absorber ID will decrease about 15% due to lower solvent circulation needed to capture the CO2. And bear in mind, this analysis does not consider a lower feed gas flow rate, which is also a potential for these proposed configurations. So to recap, we already discussed several obstacles in the decarbonization of gas turbine application, particularly the challenges with low CO2 and high oxygen concentration leading to higher costs for CCS installation. Adding to this, there are also growing pressure from the industry to achieve a higher capture rates above 95%, which further worsen the CCS especially when using generic solvents like MEA. To overcome these hurdles, it is essential to leverage BASF OASE Blue technology, which offers advanced amine formulation with capability to achieve 99% CO2 capture rate while maintaining economic viability. Other than that, the technology offers significantly lower regeneration energy and solvent makeup rates, which known to be the key OPEX indicator to justify CCS investments. To further reduce the cost, we also talk about several optimizations that can be implemented into the CCS flow sheet, mainly reducing the regeneration duty and also increasing CO2 concentration in the feed gas to the capture sections to reduce further on the CAPEX and OPEX of the CCS installation. We also explored several new configurations in the bigger flow sheet, starting from simple ones, supplemental firing, and also progressing into EGR, and also progressing into the more sophisticated configuration like selective EGR. And this configuration have the potential to significantly reduce both CAPEX and OPEX, making it more attractive to implement CCS in gas turbine applications. That's all for now. Thank you very much.
Thank you, Mohamed. So I would like to open the floor for any questions or comments you may have. Please raise your hands and introduce yourself, name and surname, role and company you represent. So the floor is open. Thank you again, Mohamed, for your presentation.
No problem.
Okay, I see Khalid. Please, Khalid.
Hi, I'm Khalid Parviz from BP. I have a question. What sort of net efficiencies can we expect going forward from a CCGT with post-capture like this? I'm just interested in your ballpark estimate.
So, I mean, as mentioned in my slides before, we talk about there is reductions on net efficiency, right? On the CCGT, which we know is about 50 to 60%. And we expect, I mean, that number there will be a penalty of about few percent to implement a CCS, depending on what solvent is being used. But for OASE Blue, we know this is actually a advanced formulation, amine formulations. We know that the energy required will be a lot less, significantly less than the generic solvents that actually is currently the benchmark for CCS installations. But I couldn't remember the exact number but I can actually send you something as well later after we finish the call.
Yeah, I guess the root of my question is that you're competing on a market. And I think it's very hard to dispatch a plant if it's going to have a few points of efficiency knocked off for the sake of carbon capture. And also it's competing with renewables. So it's very hard to put it in a competitive market. So just interest. So the higher the efficiency we can get, obviously, the better, the more dispatchable it's likely to be.
And I believe, I mean, the idea is definitely to maintain the efficiency that you have at the moment in your CCGT plant, right? But of course, I mean, it's kind of inevitable to actually, there will be some penalty, right? But of course, it depends, like I say, on the configuration and the flow sheet that to be used, whether there's an integration of renewables or carbon capture and all that will actually affect the whole flow sheet. Yeah.
Sure. Okay. Thank you.
Thank you, Khalid. Stefan, please.
Yes, Stefan Jouen, Total Energy. Naive question. I'm part of the technical committee of Technological Center of Mongstadt. And why, as your competitor, you never been to TCM to demonstrate, let's say, more publicly the performance of your solvent in terms of energy or at least emission?
Good question, I'll be honest. But I guess, I mean, there's more to, I would say, our business decisions moving forward in terms of the solvent, because as you know, I mean, we did our, maybe in the slides, we did not talk about our development, stage, because we started our solvent development way back in 2009, being a chemical company. So maybe back then we have done a lot of work already, and maybe at that stage we probably believe at that, I mean, there's no justification for us to do the test at TCM, but of course, I mean, we are open to discuss further, and we can talk, after the webinar's finished.
Thank you.
Thank you, Stefan. Paul.
Hello, this is Paul Damasio. I'm the Chief Engineer for ProEnergy, and thank you for your presentation. Have you estimated the cost of the supplies like the amines to operate per megawatt of the plant?
What do you mean by cost per megawatt? As in the regeneration efficiency, or?
Well, the plant operator is interested in what is the total cost of operating the system while he's running, right? So any consumable materials he would need to purchase, and so what cost would that add to his operations?
Yeah, in general, there are the two big OPEX that actually, when running a CCS plant, regardless of any applications, there are two. Number one is your heating media, either you have a steam or heating oil to regenerate the solvents, which is the biggest cost typically. And the second one would be the solvent consumption rates. Yeah, this is actually where, I would say, the difference, the main difference between using advanced solvent formulation versus generic solvents. Yeah, so because for us, generic solvents, the consumption rate is way higher than what we have, which means that will definitely affect your OPEX when running the whole facility in the next 20-25 years. Yeah, and of course, I mean, that number, it varies from application to application, and also how big is the size of the CO2 plant, which I'm happy to talk, in details if you want to. And just to be clear, when we actually offer our technology, we have to work with our engineering partners, because they are the one helping us to detail out the designs, doing the analysis, and doing all that. And and from there you will see, how much it will cost to install this combining the CCGT plus an OASE Blue unit on site.
Right. Thank you.
Francesco.
Good morning, Francesco Gregoriadi, Senior Engineering Director, Baker Hughes. Trailing on the same question on cost, Mohamed, do you have any figure or any case study you may have made on levelized cost of capture for your technology that you can share?
Yes, we do, but I don't remember on top of my head at the moment, but we do have a few papers that have been published. Mostly, I would say, in the coal-based power plant, where we already published a few papers, which I'm happy to share. Please do reach out to me, and I'm happy to share the papers with you.
John.
Hopefully that answered the question.
Oh, sorry. John, good afternoon. Please, you're muted. Wait.
Yeah, I'm mute.
Yeah, I cannot
Still
unmute you. I think you have to unmute yourself.
Yeah,
all right,
yeah.
now I hear you.
Can you hear me now?
Yes.
Yeah, okay. John Oakey, I'm Professor of Energy Technology at Cranfield University. So I have a couple of questions. In terms of the operation of the unit when you're operating at part load, I didn't see any figures to give me any idea of the relative performance of the unit as the load on the power plant changes. So I'd appreciate your comments on that. And secondly, the option for selective exhaust gas recycle, I looked at this around 10 years ago, but one of its limitations is that you're leaking some of the flue gas to atmosphere, so you're never going to be able to achieve the very high capture rates. Do you have an idea of what the maximum percentage capture rate would be with that configuration?
So let's address the second question first. On the selective EGR, I mean, from our experience, I believe we have done some work previously, and as you know, with the previous work, mostly around 90 to 95% capture. Not yet up to, not like pushing it to like above 95%, which actually can be a challenge as we speak. Yeah.
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 Yeah. No, I understand that.
Yeah. With on the first questions, is on sorry, what was it again? Remember now.
It was the impact of part load, because turbines run at different loads in their operating cycle. So what tends to be reported is, you know, the parameters when you're operating at full output or some nominal output, rather than looking at the way in which it varies as you change load on the plant.
Yeah. I mean, the good thing about solvent units, they are actually flexible to a certain extent. But typically, I would say that the partial load operations, the turn down rates is likely, I would say, around 30 to 40%. Yeah. Mostly limited by the distribution of solvents in the absorber columns. Yeah, which can be addressed mechanically. Yeah, but of course, I mean, let's say if the turn down rates need to go lower, then of course, I mean, there must be changes has to be made within the columns mechanically. Yeah, to ensure solvent distribution, because of the solvent circulation rate is very important to ensure that it can meet the desired capture rates, right? So,
Sure.
and these changes can be made easily. Of course, there will be costs associated with it. And I know there are also a few papers that have been published in the market talking about, you know, how we can address these partial loads, you know, installing like a buffer tanks, you know, on the lean side, on the in the solvent-based unit to, you know, address these concerns. Yeah, but there are a few that we have looked at. But of course, I mean, nothing is, you know, possible, and it can be done. Yeah.
Okay. Thanks.
Ramon, please.
Yes, I am Ramon Fuladi from Arcadis company, energy consultant, and I would like to know, in continuation from the last question, I would like to know whether this system are compatible with the scenario working of the combined cycle power plants for frequent start and stop. Maybe night shifting working or some two shifting working, whether it is compatible with such a scenario or not.
Well, very similar to the previous question, yes. I would say, I mean, again, I mean, the process, I mean, the solvent-based unit, it is flexible to a certain extent, right? But the things like how much of, like, you know, how many times that it has to go up and down, that matters, obviously, right? And how, because it takes time for the system to reach steady state, right? To ensure the CO2 is being captured properly. So I would say that this needs to be evaluated, you know, on a case-by-case basis. But in general, as I mentioned before, there are ways to manage it, and we can look into it. But of course, there will be costs associated with it to ensure that the unit, the carbon capture unit, can be operated, you know, smoothly in the long run, taking account into all these changes.
Yeah, and it is possibly maybe to use to increase the usage factor of the for the catalyst. Maybe such a scenario increase the consumption rate of the utilizing the catalyst. Is it possible or not? It doesn't matter.
No, normally at a partial load, the solvent is already overperforming. Yeah, so that's why we can reduce the solvent circulation rate. That's where the mechanical limit will be tested. So that's why we need to know how low you're going on the partial load. Is it going to be like 10% turn down, or is it going to be like just 40% turn down, right? So these are the things that we need to evaluate. And as I said, there will be impact on the mechanical limit and on how the packings, the distributors in the column how the designs of these equipments during the engineering design stage.
Yeah, okay. Thank you.
Thank you. Is there any further questions to the presentations? Also, any comments?
Nicola, there's one in the message. I'm also interested from Chidambaram. I'm also interested in the drop on CCP efficiency from the use of this technology. Is it possible to share the research papers? Yeah, we'll do that. Yeah, if Nicola, if you can send my contacts to Chidambaram, then I'll be happy to get in touch. Yeah.
Thank you, Mohamed. Appreciate it.
No problem.
Yes, if you could share with me, Mohammed, the material, then I could send it to all participants. That would be great. Thank you. To all participants, please feel free to speak up. We may not see the chat. We may not be able. Is there any?
Sorry.
Yeah, Laurent.
Yes. Good afternoon. I have a question about NOx. What is your specification at the entry of your unit?
Yes, we do have limits on contaminants like NOx, especially, right, for gas turbine applications. I mean, I'm not able to share that information, to the market, or in this case, to the webinar participants, because we normally will need to sign an NDA before we work on a specific inquiries. But feel free to reach out. We'll be happy to, supply and give you that information.
Thank you.
Thank you, Laurent. Any further comments, contribution from our audience? So I do not see known from our end. So I think it was solid discussions with our presenter. So thank you again, Mohammed, for your presentation. And we are happy our members are providing concrete solutions to the decarbonization of the gas turbine assets, and that they can provide, they can share these examples to our community and also outside. Before concluding this webinar, it is very important for us to understand, to receive feedback, to improve our future episodes, because this episode on CCS is just the first one of hopefully a longer webinar series. We're already in touch with a potential second presenter, but before concluding the first one, we would like to ask you to complete a short questionnaire. It is just 3 questions, which is done through Slido. So I will now start the interaction. So you have just received a notification on your chat, and this is the short questionnaire where you are asked some opinions about the webinars, and also yes, we are very open to your comments. So please feel free to complete the questionnaire in the following minutes. In the meantime, if you have any further comments, feel free to again take the floor, identify yourself, and simply ask the question you have. Actually, I would have a question to all our attendees of the call. I do not know if anybody of you would like to suggest any thematic webinar for the future on CCS. If you have any suggestions as well, they will be well taken into account. Okay, I do not see many other responses to the Slidos. Well, we already received 27 votes. Well, almost 30 now. Considering the participation we had today, which was very large, we are happy with the feedback, and we will make sure to include it in our, well, to address your comments in our future webinars. And once again, thank you for your time you dedicated for our first episode. And we are looking forward to welcoming you to the second episode, which will take place at the beginning of autumn this year. Thank you very much. Thank you very much, Mohamed, again, for your effort.